Thank you and welcome all to our webinar on driving through autonomous vehicle feature development. It's an immense pleasure to present this webinar jointly with the TCS team on their autonomous driving technology with reference to autonomous valet parking developed using MathWorks application. For this session, we have an intellect lineup of product experts taking us through the technology. Let me introduce you to them, starting with Mr. Abhishek Shukla. He's the research lead at Autonomous Driving Center of Excellence at TCS. With his 15 years of exhaustive experience in multiple automotive OEMs and Tier 1s, he has led several successful product deployments around diagnostic tool development, AD domain controller development, and verification and validation for AD features. Additionally, he has 2 patents in AD verification and validation methodologies and has represented TCS in various automotive conferences. Our next speaker is Mr. Akshay Saraf. He's a solution architect at TCS and primarily focuses on developing next-gen autonomous vehicle algorithms. With 17 years of experience, his research areas include designing and improving sensor fusion, path planning, localization for autonomous valet parking, and other autonomous driving features, and has been extensively working on digital transformation for virtual vehicle validations as well. Our third speaker is Dr. Rishu Gupta. He is a senior application engineer at MathWorks India. He primarily focuses on automated driving and artificial intelligence domains. Rishu has over 10 plus years of experience working on applications related to visual contents. He has previously worked as a scientist at Gsoft India in the R&D unit. The session is for 60 minutes, and in the interest of time, we'll have the Q&A session towards the end. However, please feel free to use the chat function in case you have any questions. Thank you. Over to you, Rishu.
Thank you, Prashant. Good morning, everyone. Good afternoon and good evening. Welcome to the webinar for driving through autonomous vehicle feature development. Today, we are going to talk about in the webinar different levels of automation as proposed by SAE. I'll also introduce the concepts around development of automated driving systems. Then Abhishek and Akshay will talk about how they have used MATLAB and Simulink to build autonomous parking valet feature grounds up. And then we will talk about TCS in autonomous driving and how at MathWorks we can support you in your journey of automated driving. Now, we are on the road to autonomy. And if we look from the lens of different SAE levels proposed by Society of Automotive Engineers, there are 6 different levels of automation, starting from L0, which is no automation, to L5, which is full automation. If we try to bifurcate these different levels of automation, level L0 to L2 are more of a driver support features. You are driving whenever these driver support features are engaged. In the L0, there is entirely no automation. L1 is where you will have either lateral control or longitudinal control of the vehicle. L2 automation is where you will have the features of both lateral as well as longitudinal control. Some of the features for L1 could be lane keep assist, adaptive cruise control, whereas for L2, it could be autopilot such as traffic jam assist. When we go above in L3, L4, L5 automation, these are more of an automated driving features. And these features can drive the vehicle under limited conditions and will not operate unless all required conditions are met for L3 and L4. Some of the applications for L3 could be traffic jam chauffeur or autopilot for parking or highway assistance. For L4 automation, these are more L4 and L5 automation. These are more of an automated driving features which will not require you to overtake driving at any point in time. L4 in L4 in L5 precisely, this feature can drive the vehicle under all the conditions, whereas in L4 there will be limited conditions in which vehicle can autonomously drive. Next slide. Now, when we talk about the landscape of development of an automated driving system, it requires multidisciplinary skills. You would be working on different areas like perception, localization, path planning, navigation, sensor fusion, as well as you will be working on building your controller logic pertaining to the application that you are working on. Now, if you are working on these applications, virtual validation or virtual testing becomes very important. And to do the virtual testing, you will need to create virtual world. And those virtual world will consist of scenes, which could be static in nature, can be created by tools like Roadrunner, and scenarios wherein you may want to test your ADAS features or applications. On the vehicle side, it could be the vehicle dynamics itself and also the sensor models that would be required to perceive the virtual world. While you are doing the application development around automated driving system, you would be working on lot of different pieces like I mentioned, and there will be different stages to it, like starting from analysis to simulation, designing your algorithm, deploying your algorithm to the target of choice or different embedded targets, integrating all of these pieces together and going for validation. Those validation could be as simple as model in loop validation. It could be software in loop validation where you are generating the code for individual components, or it could be hill test bench. Now, TCS would talk about how they have leveraged MATLAB and Simulink as a tool chain to establish the entire infrastructure of automated parking valet, starting from algorithm development to virtual validation, and how they have also taken the entire application for hill test bench. Over to you, Abhishek.
Yeah. Hello all. Welcome to today's webinar. So in this session, we will explain how we have developed autonomous valet parking feature with the using MathWorks toolchain and deep learning technologies. So on this slide, we show is a typical valet parking, human valet parking basically. So found on say malls or somewhere. So you have a drop-off location. You have a parking zone, and a human driver usually takes your car from the drop-off location, and he will go and drive the car and search for the parking open slot and will park your car. So to achieve this autonomously, we have developed autonomous valet parking, which is a SAE L4 feature, level 4 feature. And we have made an Android app which helps to achieve the same, to trigger the same. So in this case, now the driver drives the car to the drop-off zone and leaves the car here. Then he or she initiates the parking maneuver, valet parking maneuver using the connected app. The car will then itself drive to the parking zone here and will search for the open slots. So to do this, it will do the path planning, and then the car will autonomously drive itself to the parking zone and then will park the vehicle in the slot autonomously. So this is how basically we can achieve the autonomous valet parking feature. And L4, as there's no driver inside, so that is being depicted here. So while doing this feature, there were some good challenges which we faced because roughly we started working on this during the lockdown, and we wanted to first say test in the virtual environment before going to the office to test this. So that will be covered up in this session. Also, some of the challenges like the absence of GNSS or global navigation satellite system or GPS, which are not available in the confined structures like parking lots. So such challenges were also taken care of during this development, and we will explain this in the subsequent slides. So moving to the next slide. So how we started this from ground up. So what is my basic sensors which I need to design a autonomous valet parking? So this slide is showing you a typical installation of various sensors which we have used to implement the autonomous valet parking feature. So the first one in this case is a front camera, which is typically mounted on the windshield. So the camera which we have used has like 48-degree FOV. The second sensor we have used is a LiDAR, and we have used three of them. Two of them mounted just at the A pillar above uh, the wheels. The front one is in the grill. So these are the three solid-state LiDARs which we have used. The third sensor we have used is the ultrasonic sensor, and we have 6 rear ultrasonic and 6 front ultrasonic sensors. The sensors we have used has a minimum object distance detection of say 0.15 meter and maximum of 5 meters. The fourth important sensor in this case is a wheel speed sensor. The wheel speed sensor we have used uses a laser beam and calculates the accurate longitudinal distance traveled by the wheels. So, and along with these sensors, we have our domain controller installed in the car, as well as an in-vehicle PC, which has a GPU to run our image processing perception algorithms. So this is a typical sensors which we have used to achieve this feature. So now comes the software architecture. So this slide will tell us a high-level software architecture which is needed for autonomous valet parking feature. So as with other autonomous features, it consists of 4 main modules, which are perception, sensor fusion, path planning, and controls. So perception module basically, or submodule. Perception submodule in this case takes input from our sensors like ultrasonic camera, LiDAR, and they detect the free space. For example, they detect obstacles like pillars, cones, humans, pedestrians on the road, and parking lines. The next module, which is sensor fusion module. So what is a fusion basically? So fusion is a phenomena wherein by combining the inputs from various sensors, a better model of the environment can be generated with enough confidence for enabling such ADAS features. So this is a typical definition of a fusion. So basically each sensor is giving some type of output with some confidence values, but we want to determine the best out of them. And I want to create a best model of the environment around me. So that is what fusion in a very nutshell is, and that is used to create a fused location for all the objects which the car can see. So we use it to detect objects, lanes, and classify them into like vacant parking spaces, or we classify them into obstacles, as well as we calculate their lateral and longitudinal positions. In the same module, localization is also performed based on the inputs from the odometry, and which is compared continuously with the map data, which is also coming to the same sensor fusion module. The next module is path planning and maneuvering. So based on the parking map and the object information trajectory, the route is planned and maneuvering is done based on the LiDAR or camera data by capturing the vehicle, uh, by centering the vehicle to reach the parking zone. After the car reaches the parking zone, it starts to search for the free space. And along with this, vehicle simultaneously will do the alignment or heading correction. So as we saw in the first picture, right, we reached that parking zone and we are searching for the slot. At the same time, we are trying to align the car also, or correcting my heading. After we have found a free slot, the vehicle will start the parking maneuver to park in the identified slot. And here our patented Ackermann steering based model is used to do the parking. And then once the car comes inside the slot, final alignment correction is done based on the vehicles in the adjacent slots. Last, but one of the most important module is the controls module. So this module has three basically main sub-modules which we have shown here. First one is the AI-based steering control. Again, this is a patented algorithm by TCS that controls the steering angle by controlling the steering motor. Then we have a AI-based speed controller, which controls the speed and brake controls. And last is the shift controller submodule, which controls the shift either to command it in the drive or the reverse. So as stated earlier, this is a very, very high level overview of these modules. And some more insights will be explained by my colleague Akshay in the subsequent slides. Okay, so now in this slide, we'll talk about the typical AI workflow which we have followed for development of the perception module, submodule in the autonomous valet parking feature. The first step is the camera calibration and the data recording. So in this case, a set of images from checkerboard or even scenes are taken and they are used to calculate the intrinsic and extrinsic parameters of the camera. In this case, we use the MATLAB camera calibration toolbox. The extrinsic function, basically, it gives you the rotation matrix or the translation vector. The second step is preparing the ground truth data. So ground truth data, we have to collect lot of videos of the scene where we want to detect the point of interest. For example, this pillar sticker or this parking barriers we want to detect. So we collect lot of data with the images of these point of interest in different lighting conditions and so on. And this data is annotated to mark our point of interest. Once the ground truth is ready, or that is used to basically prepare the ground truth data. Then the third step is training the model. In this case, we have used the YOLO V2 model, and that is trained. So this is a basic phenomena wherein a neural model with different layers is developed automatically using the MATLAB toolkit. So how it is done, basically at a very high level, basically we can say that we use this YOLO V2 model, which was again MATLAB out of the box model with default parameters. And then YOLO, basically, as you may know, is stands for you look only once. So such kind of model is good for real-time processing. So we have used, that's why we have used YOLO V2 in this case. We can design a custom YOLO V2 model layer by layer. The model starts from feature extraction layer, and which can be initialized from a pre-trained layer. For example, we have used ResNet 50 in this case. The detection subnetworks consist of a series of conv, batch, norm, and ReLU layers, which is followed by the transform and output layers. So we have used, in this case, is YOLO V2 transform layers and YOLO V2 output layers. YOLO V2 transform layer specifically transforms the CNN output into a form which is required to produce the object detections. Whereas the YOLO V2 output layer is very important here because it defines the anchor box parameters. And basically, anchor box is nothing but like the bounding box. So when you give it an input, it will give you finally an anchor box wherein you get the position, the real world coordinates of the pixel coordinates of the objects of interest for which the model has been trained for. So in this case, we have trained the model for 26 classes. We have used 2000 data points for each class, out of which 1600 was used for training and 400 for testing. On an average, we were able to get like almost 98% test accuracy and for the detection of these 26 classes. Okay, so this was a very nutshell description of the YOLO V2 architecture. The next step is that from this model, we have to generate the code. So for that, we have used GPU coder toolkit, and basically this step is done once your model is trained as well as evaluated. So once it is done, we can generate the code from the using the GPU coder. The fifth step is the actual deployment of this algorithm. So in this case, the algorithm, after we have generated the code, we deployed on the in-vehicle PC, which we saw, which has an NVIDIA GPU. And in this, the car can estimate the distance at runtime. And you can use something like a transform point forward, like a forward geometric transformations to calculate those type of distances. So that is all about how we use AI for the perception modules, and this is a very like a bird eye view of how it is done. Each steps in itself is a big topic, and but most of the things we have taken, like the model and the parameters, we have taken as a default parameters, which came with the model out of the box from MATLAB. So with this, we were able to achieve the 98% accuracy for at least these classes which we trained it for. So this was about the perception submodule. Now I will hand over to my colleague Akshay, and he will walk you through the details of the sensor fusion, path planning, and others, how we have validated it. Yeah,
Hello,
over to
Abhishek.
you, Akshay.
Please let me know my voice is audible.
Yes.
My screen is visible.
Yes, Akshay.
Yeah. Okay. So we'll be covering the remaining blocks of the architecture, which has been shown in the earlier slide. And this slide is about the perception and sensor fusion. So as we can see, for autonomous vehicle, it is very important to perceive the surrounding environment or the object information. And that is done with the help of three sensors. Like here you can see the camera sensor, lidar, and ultrasonics. So how that data is extracted out of the raw data or image has already covered by Abhishek using deep learning techniques. Now once we have the engineering data, that is the object position, their type, velocity, we need to fuse these data so that we can increase the confidence in the getting surrounding information. So the accuracy of the fusion algorithm relies basically on how accurately the data is aligned. So various sensors give the data at various timestamp and also with respect to their mounting position and angle. So example, we can say a camera gives the data every 70 millisecond and ultrasonics gives every 10 millisecond. So we have to do a time and a spatial alignment before the actual fusion takes place. And that is done with a precise estimation algorithm block like Kalman filter. So once we have the data, the aligned data, we have to do a data association. So which object information of camera belongs to which of lidar sensor and which of ultrasonic sensor, that has to be done. After the object data association and merging is done, we have the final output or the fuse output, which is given to the next stage or next algorithm like localization or accurate estimation, position estimation to avoid the collision, the free space detection, and the orientation estimation. So in the autonomous valet parking, fusion plays a important role, considering there are some scenarios where in the parking there is a low light, but we are able to detect based on the lidar ultrasonics and uh, so on. So this was about the sensor fusion. I will be moving to the next block, that is path planning and maneuvering. So once the environment is perceived, the next step is to do a path planning. So I have taken the same example which was explained by Abhishek. So we have to go from this drop-off zone to the parking zone. This is done with the help of path planning. Okay? And to achieve this path planning, we will need the map of the parking lot, which we have prepared with the help of sensor itself. So we can see this we have done with the simple step. The first step is we have to identify the parking entrance, which is done with the help of GPS position. Then we need to go to the straight, then take one more left turn, and then to the final parking zone. Now, when I am explaining this, it looks to be very simple if a human driver is going to drive it. But this has to be planned by the autonomous vehicle, and this is done by implementing the small steps of maneuvering or the trajectories. And to implement this, it requires three complex algorithms. So first is, of course, we need to do a path plan. So we cannot do from this drop-off zone directly to this parking zone. And we should take in consideration the objects which are present. So object detections, the pillars detection, the barrier detection, that algorithm plays an important role. Second is we are in a covered parking. We don't have the GPS position which will tell us where we are, and we have to implement a precise and accurate localization algorithm which will tell us where we are on the prepared map. And third one is the steering and the speed control, which will make us to follow the trajectory which we have planned. Going to the next, I have captured a high level functional architecture of the path planning and maneuvering block. So here we can see with the help of camera and lidar, we have identified the objects, that is pillars and barriers, and odometry gives the accurate ego vehicle XY position, and based on the object's lateral and longitudinal distance, the XY position and the stored map, we have to define the reference trajectory. That is a combination of XY points which we need to follow. And then next block is to identify the deviation. That is how much we are deviating from the reference trajectory. And based on the error, we calculate the steering or the speed control output, which will ensure we are moving on the same trajectory which we have planned. So this was the path planning and maneuvering block. Going to the next block, and I will say that is the last block of the path planning, is the final path plan and getting the vehicle into the required free space. So here we can see we have used the Ackermann steering model, which takes the information based on the free space and prepares the trajectory, and based on that we need to calculate the steering angle so that vehicle will be parked safely in the available slot. In these cases, on the right side, I have taken few examples where there are some situation where we don't get the accurate information from the sensors like ultrasonics, and we may not be able to park the vehicle properly. In such cases, we have to do a multiple maneuvering, a re-planning of the trajectory, and the reactivation. This is the example we have taken for the perpendicular parking. For angular parking as well as parallel parking, there are more complex algorithms are involved, like clothoid curve based uh, path planning and trajectory planning. Moving to the next block, which is the control, which is required to accomplish the autonomous valet parking. This is neural network based control, and I have captured a high level workflow. So first step is to prepare a data in real as well as in virtual environment. So when I say the data is for creating a steering control, we need to record the data with various lane width, curvature, heading angle, and for that, what is the ideal steering angle required? Once we have this data, we need to give it to a neural network toolbox, MATLAB toolbox. And once the training is done, we create a Simulink block, and that block is placed in a larger control of the autonomous valet parking. So I will quickly go through the steering controls, which is a feed forward and a feedback control. Both are neural network, and based on that, the radius of curvature, vehicle speed, and the current offset, we decide what is the steering angle required to meet the requested target. Second one is the speed control, which is basically engine control as well as brake command control, so that we can achieve the requested speed. And coming to the steering control, we have filed the patent and it's already granted, and I am happy to inform that we have used it, we have verified it in the existing use case which we have taken. Going to the next is how we have validated this whole valet parking. So first step is the model in loop or a software in loop validation. So we have to create the environment. When I say environment, we have to create a virtual parking scenario, which we have created in a Roadrunner software, which is exported into Unreal Engine 4 for co-simulation. The sensor model and the vehicle dynamic model are created in MATLAB. Of course, the control algorithm is running in MATLAB, and this whole system is running in simulation. We will show the video for one of the simulation based testing. Next is the hardware in loop validation, where the ADAS algorithm will be running on a ADAS ECU embedded platform. The virtual sensor vehicle dynamic model will be running on real-time platform as DSpace. The virtual scenario as it is can be moved to the DSpace hardware. So here, along with some functional testing, we have done some performance related verification. So now I would like to show the output of the simulation based testing. So here we can see the video, which is for co-simulation between Unreal Engine and the control algorithm running in closed loop. We have tried to create the virtual environment as it is based on the measurement taken from the real parking. We can see vehicle is doing a lane centering algorithm, trying to keep it at the center. Based on the localization, we came to know where we have to take a turn. And we can see here, this was how we did a tuning in the simulation. So we can see vehicle is trying to correct itself so that it can be at the center. Now we have reached to the destination, and now the vehicle is looking for the free space available based on the parking lines, based on the surrounding park vehicle. And once it has identified, the final maneuvering or parking will take place. Now this exercise has helped us a lot before we went on the real vehicle. Now I will move to the next slide where we have the demonstration on the real vehicle and the real time or the embedded platform. So here we can see from the drop off zone, vehicle has started maneuvering. It has entered in the parking zone, and here we can see the pillar detection, barrier detection, on based of which the localization is working. We can also see the control algorithm, which is smooth compared to what was in the simulation. So we have tuned it. The localization also we can see we are turning at the right point. And even though we don't have much visibility of the line marking, based on the objects, we are able to do the lane centering. I'm just correlating with the simulated one. Now here we comes in the designated parking zone, and now we will search for the free space available or the last free space available, I will say. Now while moving, this vehicle is sensing and preparing its own map for the free space. Now we can see the vehicle is getting parked. So this was the vehicle testing validation. Okay, so now moving to the next, we would like to have a quick poll question. So I will be reading the questions and the options will be visible to you. So question is, would you like to receive the further information on any of these topics? Options are scenario creations with Unreal Engine, Roadrunner, data collection, data annotation and preparation, which is required frequently for the training your algorithm, the deep learning and perception algorithm itself for camera, lidar, radar, the sensor fusion algorithm for which the accuracy is the highest important thing. Option E is planning and control algorithm to maneuver and to do the final control. And last one is the virtual validation for doing a hill testing.
Could you please push the poll question as well?
Yeah, just a minute.
Yeah, thank you.
So I have opened the poll. Can wait for.
Awesome. So you can go inside the polling window and there you would see the poll question. Please help us with the poll responses. We'll take a pause for a few seconds so that when we restart, everybody is on the same page. Actually, we can restart. The poll question would be there for another 40 seconds. So please help us with the poll questions. Yeah, please go on, Abhishek. Akshay.
Okay. So issue my slide is still visible.
Yes, Akshay.
So So far we have covered the levels of autonomy, development of automated driving system with MATLAB, and we have taken one example, which is autonomous valet parking. We have explained. The next topics is TCS in autonomous driving and the MathWorks products in autonomous driving. So I would like to go for the slide. This slide gives the overview of TCS capability in autonomous driving. Here we can see we have 14 plus years of experience with 15 plus customer engagement across the globe. We have 50 plus AD-ADAS application developed, out of which 40 plus are in production. We have almost 1,200 ADAS engineers working across various clients. We have our own innovation team in the autonomous driving field, where we have 25 plus patent files in sensing and control algorithm. And on the right side, we can see the 4 major areas where we work. First is the sensing algorithm, the AI and machine learning based camera, radar, lidar sensing algorithms. Besides that, there is a control and perception. So we have the sensor fusion framework, V2X based algorithms developed. Third one is the data collection and analysis. So we have few solution accelerator like cloud-based data annotation, labeling frameworks. We have a data acquisition and management tools. And the last is the hills or vehicle testing. We have the virtualization frameworks, which is getting popularity nowadays, and the vehicle ECU testing, plant model creation. And as a whole, we can see we have end-to-end autonomous vehicle development capabilities. Okay, so moving next to the, I will pass the control back to Rishu for the MathWorks toolboxes.
Thanks, Akshay, and thanks for such a nice walkthrough with the autonomous parking valet application. It was very detailed. Thank you very much. Now, bringing it all back together, when it comes to the MathWorks investment in automated driving applications, we are heavily invested in the entire end-to-end workflow for autonomous driving or automated driving. Initially, like I spoke about, it is a multidisciplinary skills requirement when it comes to development of automated driving. So there are a lot of products in the MATLAB and Simulink family, starting from automated driving, deep learning, sensor fusion and tracking, control systems, vehicle dynamics, depending on where you are in your development cycle and what are the workflows that you are looking at. If you are just getting started, probably automated driving toolbox will give you very good understanding and very good starting point for developing ADAS features. There are a lot of reference examples available which you can use to get quickly started. If you are working on perception piece while trying to do artificial intelligence, deep learning, there is a dedicated capability around deep learning toolbox which will help you to work either on radar, lidar, point cloud data, camera data, or any other kind of sensor data that you are working on. While you are working on sensor fusion algorithms, you could be getting detections from multiple different sensors. It could be radar, lidar. You may want to fuse those sensors to create unique tracks for individual objects. So there are a lot of out-of-the-box trackers available. There are capabilities which will help you to create your own tracker with the help of sensor fusion and tracking toolbox. Similarly, if you're working on controller logic, then control system toolbox will help you to build the controller logic for your application. Irrespective of what kind of controller you are planning to work on, whether it is simple PIPD control, PID control, or it could be as complex as nonlinear MPC control. Now, vehicle dynamics block will help you when you are going for modeling your dynamics. Automated driving toolbox itself gives you accessibility to simple 3 degrees of freedom bicycle model. If you are looking forward to building a very high fidelity vehicle dynamics model for your own vehicle, that is very much possible. Then once all of this is together, and whether you want to go for virtual validation or hill testing, or you want to generate code which can be deployed onto your actual ECUs, there are a lot of coder products that can help you do that. So you can generate code, C++ code or target specific code directly from the applications that you have implemented in MATLAB and Simulink. On the virtual development or virtual platform side, there is a Roadrunner product which help you in scene creation, which we have used to create the parking valet scene. Can you go to previous slide?
Yeah, sorry.
Yeah, which will help you. Yeah, which will help you to create scenes for the virtual validation. Also on the right, you can see Polyspace, which will help you in code verification or code debugging while you are doing the algorithm development. There are a lot of workflows if you're working on some other tools as well, because automated driving is has a very huge landscape. So you could be working on a lot of other tools. So there are a lot of capabilities in which you can co-simulate, co-integrate as well. Next slide. Now, while you are doing the journey for automated driving, there are a lot of resources which are made available from MathWorks side to get you quickly started. On the left, you can see there are a lot of on-ramp courses which could be focused toward individual applications, whether you're working on perception, machine learning, deep learning, or you're just getting started with MATLAB or Simulink. On the right side, you can see a lot of tutorials which are available at mathworks.com, whether you are trying to do model predictive control, you're trying to build a reinforcement learning algorithm, or you're working on sensor fusion or tracking, or just getting started and wanted to gather more information around automated driving. Then in the middle, you can see a lot of different courses available specific to automated driving domain. There are a lot of training courses, whether you are getting started from on automated driving or you are building your advanced applications, doing automotive system designs. So there are a lot of ways in which MathWorks can come in and help you in your journey of automated driving.
Thank you.